All right, so we're going to work through an example here using Riemann sums to evaluate a definite integral. Now, what we have here is a definite integral right here, and this is a definite integral because we have a definite interval. So it's integral with a g, a definite integral with a g, because we have a definite interval with a v from 1 to 2. Now, what this 1 to 2 is this is our values for a and b. This is where the beginning and the interval are. So if we were talking about finding, doing a Riemann sum, that would be using a or b minus a over n. In this particular instance, I'll talk about n in just a second, but that gives us our width of 1 over n, which is what it is right there. So what I'm doing right here in this piece is writing out the Riemann sum as it needs to be right there. So I'm doing the Riemann sum, and I'm using the right-hand Riemann sum. And you're like, well, how do I know whether to do the right or the left? And there's also another one called the midpoint, which just literally find the midpoint between the two of them. It's kind of a mixture of the right and the left a little bit. There's also a 1/2 piece in there. It's not difficult to figure it out. You can probably also find it easily. And I'm just doing the right-hand sum because it's the easiest one. It has the fewest pieces, and since I'm letting the number of intervals go off to infinity anyway, it doesn't matter which one I use. So the Riemann sum is the width times the height. The height is f of whatever the function is, or the function in this case is going to be x squared, and I'm using a plus the width times k, okay, where k goes from 1 to n. So that sets up my limit as n goes to infinity of the summation from k equal 1 to n of 1 over n and 1 plus k over n squared, quantity squared. Now you're saying, where did that squared come from? My function is x squared. So I'm taking the stuff that's inside of the function and I'm putting it into the function of x squared. So there it is right there. This whole piece right there, this 1 plus k over n is my x value, okay, that goes into the function. I'm going to multiply that out, okay? And the reason why I'm doing this is because some of you are asking, do I have to write the limit and the summation every single time? You do it until you use them. So the answer is yes. You write them until you use them, just like you would with a plus sign or anything else. So I'm going to take this stuff right here and multiply it out, right? And then I'm going to take that 1 over n, I'm going to distribute it through, which is where I get these pieces right here from. 1 over n, 2k over n squared, and k squared over n cubed. All right, pause the video for a moment and prove to yourself that this becomes that. And when you multiply this by 1 over n, you get that. Okay, so that's where that came from. Now what? Now we need to get rid of that summation. Luckily, we have summation formulas. And the summation formulas are going to allow us to be able to get rid of all those pieces, which is where all this came from. And you say, some of you may be thinking, that's a lot. Well, first thing is, notice the summation's gone. The summation formula sign is gone because I'm doing the summation. 1 over n is a constant. The summation formula for a constant is the constant times n. 1 over n times n. Next one is a linear one, 2k over n squared, where 2 and n squared are considered constants because we're inside the summation. N is a variable for the limit, but it's a constant for the summation. So here I'm going to be doing n plus 1 times n all over 2, which then allows me to cancel out the 2's, and then I'm going to rewrite this as n squared over n, and I'll show you why I did that here in a second. And then my last piece over here, I multiplied out those two binomials there and got 2n plus 3n, probably 2n squared plus 3n plus 1. I distribute my n through, and I get 2n cubed plus 3n squared plus n, all that's still over 6, and then multiply by n cubed. All right, so that's all those pieces. Again, pause the videos as you need to kind of absorb what's going on here, and then back up and rewind it if you need to. Now what? Now what I'm going to do is I need to write down each of these pieces. 1 over n times n is 1. And then I have right here, I have n squared over n squared, which is 1. I have n over n squared, which is 1 over n. On to the next one. I have 2n cubed over n cubed and a 6. The n's cubes cancel out. I'm left with 2 over 6. I have 3n squared over n cubed in the 6. So that's 3 over 6n. And then I have n over 6 times 1 over n cubed, which gives me 1 over 6n squared. So all I did was just kind of multiply and cancel as I went through there. Now, I'm going to let n go off to infinity, and I'm going to look at each piece individually, which is why I circled each one, right? So when I did that, as n goes to infinity, 1 goes to 1. As n goes to infinity, 1 goes to 1. As n goes to infinity, 1 over n goes to 0, right? As n goes to infinity, 2 over 6 goes to 2 over 6, or 1/3, right? As n goes to infinity, 1 over 6n goes to 0, and then, of course, the last one goes to 0 as well. Okay, so what I have there is 1 plus 1 plus 0 plus 2, 6 plus 0 plus 0, which gives us 2 and 1/3. That's what that integration works out to be. Now, something we're going to deal with in the next coming sections here, a little bit more in depth, is how to do this integration. This integration, I'll kind of give you some foreshadowing here. What we would do is the integration of x squared is x cubed over 3. Add 1 to the exponent, divide by that new exponent. I'll explain that more in detail if that's not a whole lot of use to you right now, or if it doesn't make sense to you right now. And I'm evaluating from 1 to 2, and then I just simply plug in those values. So I plug in 2 and I plug in 1, so it gives me 2 cubed over 3 and 1 cubed over 3, so it's 8 over 3 minus 1 over 3, which gives me 7 over 3, which is 2 and 1/3. Now, one of these is significantly easier to do than the other. What we're doing between these two processes, other than having the two different ways to find the exact same value, is the Riemann sum is our proof, or our the way that we establish that this really does work, that this integration process really does work. The other thing that's also going on here is if we know that integrations and these summations are more or less interchangeable, it gives us another way of dealing with integrations when this integration is extraordinarily difficult to deal with. And there are situations where that occurs. And we'll look at some of those examples in the coming days. All right, thank you very much. Have a great one.